Thank you so much. Thank you so much for the introduction, Li Wei. Well, let me take just 2 minutes to reintroduce myself. I think this is not working. The pointer. Well, who I am? I'm Carlos Lopez-Coba. This is my email. Oh, yes. Carlos Lopez-Coba. This is my email. This is my office if you want to get in touch with me. I just finished my PhD at UNAM, Mexico, studying basically the properties of outflows, AGN outflows, star forming deviant outflows. And also I did my master thesis studying star formation, galactic winds. I joined ASIAA in April, and I'm from Mexico. This is a pretty nice cartoon of Mexico. We have a large diversity of culture, food, etc. We don't only have tacos and tequila. We have many more than that. I am from this region of Mexico, of Mexico, the Yucatan Peninsula. In particular, I'm from from Yucatan, the region where the Mayan culture established during this period of time. So if you ever go to Mexico, I recommend you to visit Yucatan, in particular Chichen Itza, which is one of the 7 wonders of the world, and to visit also this place, which is Coba, which is one of the highest pyramids constructed by the Mayans, which is also my last name, and therefore I feel very proud to be part of this Mayan culture. So, I don't know what happened. Sorry, technical problems. No. I think I better change the slides with my hand. So my expertise is in this. It is not working again. No. Yes. And my expertise is in galaxies, in particular self-forming deviant outflows, AGN driven outflows. All these. Here I show you 4 pictures of different outflows showing filamentary structures of gas flowing from the nuclear regions, either driven by powerful AGNs or by star formation processes. And this is the color code that I use in this image. However, I'm not going to talk about this object in this case. In this talk, I'm going to talk about my recent project ongoing of the kinematic study of this kind of galaxies, particular barred galaxies, how I show you in this example. And this is a color image of this galaxy. Okay. And before that, let me give a general introduction about galaxies and galaxy evolution, and just to say some words about most of our knowledge, part of our knowledge about the evolution of galaxy comes from spectroscopic galaxy surveys, such as the Sloan Digital Sky Survey. Even that this survey only took the central spectrum of galaxies, but taking the central spectrum, but taking for millions of galaxies, it was able to construct ionization diagnostic diagrams, such as the BPT diagram, with the most prominent emission lines in the spectrum. This is the spectrum of the nuclear region of this galaxy, in which all this information, it was possible to construct this kind of diagrams. And this diagram, basically, galaxies are separated between galaxies with a soft ionization source, such as galaxies dominated by star formation or H2 regions, and galaxies dominated by a harder ionization source, such as AGNs. There is also another kind of galaxies dominated by post-HEV stars or harder ionization source that we don't know very well. This is the maximum starburst demarcation proposed by Keeley et al. Basically separates between star-forming galaxies and AGN galaxies. However, two-dimensional information is essential to understand the local properties of galaxies. For instance, here I show you this barred galaxy taken from integral field spectroscopy data. And here's the continuum image. In the right panel, I show you the ionized gas distribution of this galaxy. This is a really powerful, this kind of image is a really powerful to understand the distribution of gas along the or across the galaxies. This is the color code used in this image. And I'm going to use this color code in all my presentation, okay? So what we see here is that H alpha is observed in green, and nitrogen in red, and oxygen 3 in blue. And dark regions basically means that we don't have gas with good signal to noise, okay? So even that the BPT diagram was not designed for spatially resolved objects, we can trace the ionization of galaxies with integral field spectroscopy data. For instance, this blue region here, which is most probably associated with a young H2 region, is located in the low metallicity region of this diagram. And the nucleus of this galaxy is located in the BPT region, okay, of this diagram. So if we only have one spectrum, the central spectrum of this galaxy, we would classify to this galaxy as an AGN. But as we observe, there is a variety of ionization processes occurring in galaxies. Therefore, spatial information is really useful. There are many galaxy surveys and compilations that use this technique, the integral field spectroscopy technique. Probably the two most important ones are the MaNGA galaxy survey and the Khalifa galaxy survey. And these are the main characteristics. This is the redshift coverage, the spectral resolution, the number of galaxies in the survey, the spatial resolution, field of view, and the number of pixels per data cube. I'm going to explain later what is what consists the integral field spectroscopy. And I just put here the MUSE and compilation. It is not a proper survey, but it's a compilation of galaxies observed, a compilation of almost 700 galaxies observed with the MUSE spectrograph at the BLT in Chile. And this is the redshift versus spatial resolution for the most important galaxy surveys. Okay. So, sorry? 3,000 galaxies. Okay, there is a mistake here. Thank you. So probably you have heard about the integral field spectroscopy, but for those people that haven't heard before about the integral field spectroscopy, basically we obtain data cubes with two of the dimensions being the spatial dimension, the right ascension and declination, and the third axis is the wavelength coverage, okay? In such a way that we have an image of the galaxy at different wavelengths, okay? So that is the idea of the data cube, okay? So in each pixel or a spatial pixel, we have a spectrum of the considered point, and with different techniques we can recover the stellar population properties of the individual spectrums of galaxies. And for instance, this is performed with the PyPredict code, which basically what this code makes is try to model the observed spectrum with multiple single stellar population with different H's, different metallicities. So after we model the observed continuum, we get different properties of the stellar population, for instance, the age, mass, velocity, star formation rate, etc. And also we get properties of the ionized gas. So we can model the emission lines, for instance, with Gaussian functions or any other function to obtain the flux, velocity, and velocity dispersion, and also the equivalent width of the lines. Some of the outputs of this code are two-dimensional maps of the properties of galaxies. In this case, I show you this is not an output, this is just a reconstructed continuum image of this cube. And this is the emission line image color coded with these colors as well. So we observe again how H alpha is distributed across the stellar disk, showing the spiral arms, and the red one, the red is the nitrogen. We observe that the nucleus is very intense in nitrogen. So with this information, we can trace the ionization across galaxies using different diagnostic diagrams. This is just one of the most usual diagnostic diagrams used in optical astronomy that was proposed by Bejers and Osterbrook in 1987. So what I just want to mention here is that the disk from the ionized gas from the disk is basically dominated by star formation processes, and the nucleus of this galaxy is dominated by a harder ionization source that might be an AGN or might be a liner, for instance. And another output from this code are the stellar velocity and the velocity of multiple emission lines. In this case, this is the H alpha velocity, because H alpha is the most intense in the optical spectra. So far, as I mentioned before, the velocity, or the H alpha velocity, is one of the outputs of this code. And not only of this code, it's one of the outputs of the different codes that are dedicated to analyze integral field spectroscopy. So for instance, this is a Khalifa galaxy. Okay, this is the Sloan image. This is how Khalifa observed this galaxy. And we observe clearly that the galaxy is not observed with the highest spatial resolution, not even the highest spectral resolution. And this is the ionized gas distribution for this galaxy. I like to put this kind of image because it exemplifies really well how is the distribution between the continuum and the ionized gas. Okay, and because we have a lot of H alpha in these galaxies, we can trace pretty well the kinematics of this galaxy. In this case, we have a regular velocity field with a symmetric approaching and receding sides. Okay, orthogonal major axis and minor axis. So this is a very well behaved galaxy. So, and if we know, for instance, the inclination of this galaxy and the position angle, the major axis position angle, which is this one, okay, we can trace, for instance, the rotation curve of this galaxy. Only if we take some spaxel or pixels, or pixels along this axis, and we plot against the projected radius, for instance. And with these points, we can construct the rotation curve. And for instance, with the maximum circular velocity, we can with the maximum velocity, we obtain the Tully-Fisher relation, which is also famous relation. However, the main assumptions of this kind of analysis or kind of rotation curves is that circular rotation is the only component or the most dominant component in galaxies. However, we know that there are many other sources of circular, there are many other sources of non-circular rotation in galaxies that are either produced by environmental factor, local processors, or non-axisymmetric potentials. Here I just show you some examples. In this slide I show you a galaxy, a gas-trooping galaxy. You observe here the continuum image. This is the ionized gas distribution again, and you observe here tails of gas, ionized gas. This galaxy is falling in the center of a cluster of galaxies. So the kinematics of the galaxy is totally a mess, basically. The stellar bars, here again, we observe here a bar. It is not so clear because this is a galaxy observed with MaNGA. Again, MaNGA is, has a low spatial resolution, a low medium spectral resolution. So, but it is clear that we have a bar. Okay, this is again the ionized gas distribution of this galaxy. I don't put here any image about the kinematics of these galaxies. Okay, I just want you to show you how is the ionized gas distributed in these kind of galaxies. Here is another galaxy. This is a almost H1 galaxy, and in green here you observe basically the disk of this galaxy, and in the red one you observe this kind of horns associated to star-forming driven outflows. Okay, remember the colors. The colors is this one. Okay, we have also galaxy mergers. Okay, we have here the continuum image. Here we have another galaxy interacting with this one. So again, here the kinematic is totally dominated by interaction itself. We have also spiral arms. So what I want to say here is that in real life, there are many other sources of rotation in galaxies, not only the circular rotation, which is typically considered as the most dominant. However, we cannot get deep inside in all these kind of non-circular motions because at the end we are not going to finish analyzing one single galaxy if we take in consideration of these kind of factors. In this talk, I'm going to focus mainly in these kind of galaxies and also these spiral arms galaxies. This is, for instance, what is the velocity field expected for a non-barred galaxy. If there is no bar, or if there is no perturbation, basically the major axis and the minor axis, the kinematic major axis and the kinematic minor axis are basically perpendicular, as we saw in the previous slides. But in the presence of a bar, we observe that the minor axis has an S shape that depends basically on the bar position angle and the amplitude of the non-circular motions. And here I wanted to show you some images again of galaxies hosting a bar. And if you see the zero velocity line, which is in black here, the lines are isovelocity contours. You observe that the zero velocity line is totally twisted for this galaxy here again. Okay, and this galaxy also shows a large twist in the central parts. So the spatial resolution is increased in this region, in this axis, such a way that this galaxy was observed with a much better spatial resolution and spectral resolution than this one. However, this kind of features is observed in all of these galaxies. In all of these galaxies, we observe strong oval distortions. However, this kind of distortions this is not new. You already knew about this kind of perturbation. Since the 1977, this is a galaxy observed with H1 data. These are isocontours of the H1 velocity. And we observe this is in the background, there is a continuum image. And on top of this galaxy, there observe the isocontours obtained with H1 data. And here again, we observe that the isocontours are twisted around the center of this galaxy. So for first time, we can analyze this kind of movements spatially resolved. If we perform a simple circular rotation model, okay, in these three galaxies, we observe high residuals in the central region of the galaxies. Here, 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 okay? So what basically means is that a simple circular model cannot describe the observed velocity field of these galaxies. So this is the simplest model, the circular rotation model, which depends on the systemic velocity, the inclination angle, and the theta is the azimuthal angle in the plane of the disk, which depend on the kinematic center, inclination, position angle, and that's it. Okay? So even that is the simplest model, it has a large free parameters. So what we note here is that simple circular models are not able to reproduce the distortion that we observe in the central part. And such distortion are of the order of 50 kilometers per second in these galaxies. So it is clear now that if we want to study this kind of galaxies, we need to include models that take into account the non-circular motions. Okay, and for this purpose, we developed this package, which is ShockSud, which is a Mayan name, by the way, which is more or less translated like the study of the movement. This package, what it makes is performs an algebraic solution for the velocities, performs a least square minimization for the inclination angle, position angle, kinematic center, and at the end, it performs a Bayesian analysis. So at the end, we obtain this, all this information and also the velocities with this kind of with this code. This is the traditional chi-square. This is the likelihood function. Yes, the entrance of this code is basically a model that you choose between these four different models, and also the velocity map. Okay. So this code uses the entire velocity map. It makes the feed and it uses all pixels in one single feed. This is the error map. So here I just put the different models included in this code. This is the circular rotation model that we saw before. This is the radial model, which basically is the circular model superimposed by a radial term. This is the bisymmetric model that was proposed by Spickens and Selwood, which is basically was basically developed to model oval distortions. And this is a more complex model, which is the harmonic decomposition model. The interpretation of this of the harmonics are not as straightforward. However, the potential, the gravitational potential, is related with the harmonic number. Okay, so this all these models are included in this package, and here I show you only one of the outputs of this package. Here is the covariance of the different parameters. For instance, this is for a galaxy. I'm not showing the galaxy here, but one of the outputs is the position angle, inclination, kinematic center, systemic velocity, and the bar in the case that we are analyzing galaxies with bars. Okay, In addition, there are other plots like this describing the kinematic components. I mean, the circular rotation, the radial rotation, the tangential rotation, etc. But I cannot put another plot here because it is going to be too large. So now that we have the package to model this kind of galaxies, what if we model one of our bounded galaxies with a radial model? Okay, the radial model, what it says is basically this: given a given the orbit in the disk plane of the galaxy, this is the disk plane. Okay, it is not the sky projection. In an orbit, we have a rotational component given by this term and a radial term that can be either inflow or outflow, okay, depending on the direction of the flow. So if we apply a radial model to this galaxy that we know that has a bar in the center, we model really well the observed velocity field. Okay, these are the residuals. We observe some kind of residuals in this image. And this is now the true rotation curve, including non-circular motions. This is the radial term. Okay, this is a good model, explains what we observe. However, such a large velocities of a radial model are extreme. Okay, if this galaxy has an inflow, we observe gas moving at almost 100 kilometers per second moving towards the center. If this gas has an outflow, then we are observing gas moving to 100 kilometers per second out of the flowing, okay, towards the opposite direction of the nucleus. So even that this model can explain the observed velocity field, is not a reasonable model given such a large velocities. Instead, the bisymmetric model includes a perturbation along a fixed axis, which is the bar position angle. This is an schematization of the bisymmetric model. Basically, this is the perturbation, this is the bar, okay? And in the bar, we have a component, a tangential component along the bar. We have a radial component also along the bar. And we have gas moving in a circular orbit as well that is not part of the bar. Okay, this is the general idea of this model. So basically, we decouple the bar rotation with the disk rotation. And this angle is measured on the plane of the disk. So we can translate this angle to its sky projection, which is, we can measure this angle through this expression. Okay? Now, if we include the bisymmetric model in this galaxy, you observe as well that we are able to reproduce the S-shaped distortion in the nuclear region. And now we observe the movement of the bar here. We observe a bar moving with a tangential radial velocity in red here, in a tangential velocity, in a radial velocity in red, and tangential velocity in blue. So basically, there is an inflow. I'm not going to say inflow. There is a radial movement along the bar, and there is also a tangential movement. Together, the circular rotation of the galaxy. So if we perform this kind of analysis of non-circular models on galaxies, what we are going to obtain is basically the description of the bar, how the bar rotates in galaxies. However, the truth is that most of bar galaxies do not exhibit bars, does not exhibit gas along the bars. For instance, again, I show you here the continuum image, and you see that in most cases there is no gas in the central parts. Sorry, there is no gas, no gas, no gas, no gas. no gas. The colors are here as well. So if we want to perform this kind of analysis with the ionized gas, it's going to be a little bit difficult because most of the information of the kinematics is recorded in the ionized gas, in particular in gas lying along the bars. However, one of the outputs of the code is also the stellar velocity. So given that we have data that has a low spatial resolution, such as in Khalifa and MaNGA, the velocity maps in general don't have a coarse spatial resolution. What it means is that the spatial resolution is much worse than the ionized gas, because in order to estimate the stellar velocity, this is computed over different bins covering different spaxels in order to increase the signal to noise of the continuum. So this is the stellar rotation of this galaxy, which has a bar, and this is the stellar rotation of this galaxy that has a bar as well. If we don't observe any twist here, not even here. So we need data with higher spatial resolution. For instance, this galaxy is one galaxy observed with MUSE data. Okay, this is the ionized gas distribution. We observe that we don't have gas in the center, so we cannot perform kinematic models about the bar in the center. However, we observe here a twist in the stellar velocity. If we perform circular models in these two velocity maps, we observe, for instance, that in the stellar velocity map there is a large residuals in the inner part, and here we observe the twist. And in the H alpha velocity, even that we don't have ionized gas in the central region, we observe some kind of high residuals in the central region. So what is interesting here is that it seems that ionized gas in the stars follows basically the same potential of the galaxy, of the bar. And if we perform a bisymmetric model in this galaxy, we obtain again the different velocity components. And as I mentioned before, one of the outputs of the bisymmetric model is the position angle of the bar. And if we plot the kinematic position angle of the bar against the photometric position angle of the bar, which can be estimated, for instance, with an isophotal analysis with the light distribution with the light distribution, we can trace easily the orientation of the bars, basically by tracing abrupt changes in these parameters. So if we plot here the two angles, the green one is the kinematic position angle and the red one is the photometric position angle, we're going to observe that they are aligned.
You just mentioned that the gas follows the bar, but you said there is no gas in the bar in the previous slide. What do you mean by that? If the gas and stars follow the bar potential on the bottom right.
Yeah.
But there is no gas, so what do you mean by the word the gas follows bar potential?
Yeah, yes, that's true, that's correct. We don't observe gas in the center, and it is clear, but we observe some residuals here in this region, that probably what we conclude is that the gas around the bar is still feeling the potential of the bar. It is not conclusive. Probably this is not the best way to express this because we don't have gas in the center. But we also observe high residuals in the same regions. So most probably these high residuals are produced by the bar itself. But why there is no gas in the center? There is not so clear why in most of galaxies there is no ionized gas in the center.
Well, that's because you cannot have a circular motion, so you lose angular momentum, isn't it? In the stellar distribution, according to Biddy and Tomain, a bar is made out of box orbits, so you should have a high velocity dispersion. I mean, can you measure dispersion?
And in stellar velocity, no, we cannot. Well, we could measure. I don't have the data in this moment, but we have the dispersion in this one. But
and of course, gas cannot do box orbits, so gas cannot consistently satisfy a bar without just falling in.
yeah.
That's why you don't have any. At least that's what Benjamin says.
What? You have solved the problem.
I mean, to main solve this.
Yeah, I mean, yes, that could be an explanation why we don't observe gas along the bars. Okay, let me follow. When we perform this kind of analysis with a larger sample of galaxies with high spatial resolution, such as MUSE data, we observe that indeed the kinematic position angle of the bar is correlated with the photometric position angle of the bar, which is basically telling us that episymmetric models are models, or are the most ideal models for describing the kinematic of galaxies hosting bars.
But that angle, sorry, just back to the plot. The x-axis is an angle.
Yes.
That
This,
goes from 0 to 360.
yes.
So that's the angle alignment from the north to the bar axis.
Yes. This is the 0 axis. 0 degree is the north.
But isn't the maximum you can get 180?
Yes. I mean, the photometric position angle goes to 0 to 180, and the kinematic position angle is measured from the receding side of the galaxy. So the receding, for instance, the receding side of this galaxy is in this plane, in this side. So it will be 180 plus 90 plus, it would be like 345, more or less. Well, at the end, we can translate these angles between 0 to 180. Okay, but if we stick to the definition of kinematic position angle, this is the angle. Okay, which goes from north to the kinematic position. Okay, that's why I plot here 0 to 360. Okay, so there is a good alignment between the kinematic position angle and the photometric position angle. And here are just conclusions about this work.
I can understand you can measure the position angle for the kinematics, but how about to measure from the photometry?
Okay.
Because your x-axis is the photometry, right?
Yeah.
Of course, you can measure the receding side from within the 316. But how about the photometry?
We can only measure the photometry between 0 and 180.
Yeah.
But angles are, I mean, for this case, the photometric angle would be like 120 degrees. The photometric position angle, more or less. The north is here, which is 0, and it goes in this direction. It will be like 120, more or less. If you add 120 plus 180, you will get this angle. So it is easy to convert between kinematic position angle and photometric position angle. Just you need to add 180 to the photometric position angle. It is clear? Okay. Yes, because angles here just got from 0 to 180. Okay, this is just some final conclusion from this previous work, and we observed that for galaxies with high spatial resolution, if we plot the size of the bar against the stellar mass, we observe that the fraction of non-circular motions in this galaxy is not larger than the 20%, which the F means the ratio between non-circular motions over circular rotation. And now I told you that there is another kind of non-circular model that includes an harmonic expansion, and this is the harmonic model. This M term is related with the potential of the galaxy. In the case of a bar, and in the case for galaxies with two spiral arms, M is equal to, okay? No, sorry, here it is correct. For the case of a bar, M is equal to, so if we substitute M here, we will get that the only harmonic terms that contribute to this harmonic expansion are 2 plus 1 and 2 minus 1, which is this equation. That is, for the case of a bar, we get this expansion of the non-circular motions. We get the C1 term, C3, S1, S3. These are not easily to these terms are not easy to relate with true kinematic properties of galaxies. However, the C1 is closely related with the circular rotation, the S1 is closely related with the radial rotation, and the C3 and S3 measure basically the perturbation along the bar and the perturbation along the spiral arms. I don't want to get in detail with these components, okay? If we apply this kind of decomposition again to data with high spatial resolution, we will observe that we model pretty well also the inner part of this galaxy, okay? We know that this is a barred galaxy. And from previous work, we know that if we measure the ratio of the S3 versus C1 and S1 over C1, I mean, if we compute the slope of this of this relation, we know from from models of bars and spiral arms that if the slope is lower than 0, then we have a bar. If we have the absolute value of M lower than 0.1, it's a radial flow. And if we have a strong S1 component, we have a spiral flow. So for this case, it is totally compatible with having a bar. I mean, the velocity field is totally compatible with having a bar. And once that we have the circular rotation of galaxies, the true circular rotation of galaxies, we can instance compute the maximum circular rotation and try to see how if the maximum circular rotation is affected or not by circular motions. Okay. For instance, we can parameterize the rotation curve with any kind of parameterizations. And to do this kind of analysis more statistically, we use the MPL10 data. I have access to the MaNGA MPL data through Li-Hui. And this is the star formation rate against the stellar mass from nearly 9,000 galaxies. And this is the ionized gas distribution for each single galaxy, okay? Which we are basically observing that we have a sequence of galaxies forming stars or with excess of H-alpha emission. We have another sample of galaxies with basically no H-alpha emission. If we put this plot in terms of the kinematics, again the H-alpha kinematics, what we observe is that all star-forming galaxies are rotating galaxies, and we have a sample of galaxies that basically they don't have any rotation. They are not supported by rotation. And again, if we plot all these galaxies in the BPT diagram, we observe here a bunch of galaxies in the star formation region, and we have here galaxies in the AGN region. The blue means oxygen 3, remember? So this kind of galaxies has an existence of oxygen 3. So they have an AGN in the center. So when this kind of analysis of the harmonics are performed over the MaNGA data, this is a galaxy with a perturbation in the central region with 2 arms. And we can easily compute the harmonic components. But if we want to perform this kind of analysis for the whole sample, or saying in other words, if we want to perform, or if we want to trace the maximum circular rotation on this galaxy, we must include only galaxies observed with the largest bundles, because the lower bundles, the lower field of view, are more affected by PSF effects. So even though this galaxy is observed only the nuclear region of is observing only the nuclear region, we observe a twist in the center. However, we are discarding this kind of bundles, which do not allow us to measure, for instance, the maximum circular rotation of galaxies. So when we apply this analysis to of the order of 1,500 galaxies from MaNGA, if we apply, for instance, circular models, which I show you in the upper panel, and if we apply harmonic decomposition models, this is the C1 component, which more or less trace the circular rotation, we observe that the C1 component is approximately describing the circular rotation. And these are the amplitude of the non-circular motion for the same amount of galaxies. Okay, we observe non-circular motion between -50 and 50 kilometers per second. So now, this is the Tully-Fisher relation for the for this amount of galaxies. This is the maximum circular rotation, and this is the stellar mass. Okay, this is the classical circular rotation. In this case, we do not include circular motions, and we get the famous Tully-Fisher relation with a famous slope, okay, 0.3, and this is the slope. Sorry, the zero axis, and we have a small dispersion as well. But now, if we include the non-circular motions, here we observe that the slope doesn't change at all. Not even the slope. I mean, the slope changed a bit, not too much. The scatter is not reduced. So what it basically means is that the Tully-Fisher relation is stable on the non-circular motions. So these global relations are not affected by bars or spiral arms. And if we plot now the BPT diagram, which basically is a diagram that shows the ionized distribution, this is for the central region of the galaxies. We observe that this is the quadratic sum of these non-circular terms. We observe that galaxies in the composite region, in the AGN region, has the larger amplitudes of non-circular motions. Okay, this is really interesting because this can be related to the AGN processes, how the gas is carried, how is the fueling of the AGN might be related with the non-circular motion, in particular the radial motions. And finally, if we plot the integrated star formation rate against the integrated stellar mass, we observe that, again, this parameter, which basically measures the amplitude of the non-circular motions, we observe that most that galaxies that has the larger amplitude of non-sequential motions lie in the transition region between star formation main sequence and retired galaxies. So again, kinematics can be an explanation of why galaxies have a transition between star formation and galaxies with no activity or galaxies with no star formation. Probably there is a link with kinematics that we haven't explored yet. And this is this can be performed because we have a large sample of galaxies, such as MaNGA data. This is my last slide. I just want to put here my conclusion of this part. And as you observe, we addressed the presence of non-sequential motions in different data, with different spatial resolution, with different spectral resolution. We observed that non-sequential motions might be really important in order to understand the global properties of galaxies. So that's it. And just to give your attention, there is this cartoon represents this one of the Mayan observatories that was here as well more than 1,000 of years ago. And we have still this observatory. So people have been interested in astronomy a long time ago, and we are still interested. So thank you so much.
We have 3 minutes for questions. Any comments or questions?
So the last few slides is quite interesting because you sort of say, what kind of properties of galaxies are causing these non-circular motions. But my question is sort of chicken and eggs. So which one causes which? Because you have ASIAA and you cause non-circular motions, or you actually start with non-circular motions, then you cause intense ASIAA activity. Can you answer that, or